Imagine a vessel that doesn't just move through water, it glides, it hovers, it adapts to currents with a grace that seems almost unnatural. Now imagine that same craft powered by advanced energy systems, silent, efficient, and capable of speeds that make traditional boats look sluggish. This isn't a concept from a sci-fi film. This is real. And the mind behind it is Maxwell Chikumbutso. Today, we're diving into a world where marine engineering meets innovation that defies expectations. Maxwell has taken the idea of water transport and reimagined it from the ground up. Forget the diesel engines, forget the wake turbulence, forget the limitations of hull design. What you're about to see changes everything you thought you knew about water vehicles. The first thing you notice about Maxwell's designs is their form. Sleek, streamlined, almost sculptural. Each vehicle looks like it was shaped by the currents themselves rather than engineers. But this isn't just aesthetic. Every curve, every contour is optimized for efficiency, for maneuverability, and for stability in conditions that would cripple conventional craft. What sets these water vehicles apart isn't just their shape, it's the technology inside. Many of Maxwell's prototypes use hybrid energy systems, combining ultra-efficient electric motors with advanced energy harvesting modules that draw power from water movement itself. Imagine a boat that charges as it moves, extending endurance without stopping for fuel, capable of journeys longer than any traditional vessel in its class. The next evolution is control. Maxwell's vehicles are equipped with autonomous navigation systems, capable of adjusting in real time to waves, currents, and wind. Sensors map the water environment constantly, predicting obstacles before they appear, maintaining perfect balance even in rough seas. In a sense, the vessel becomes an extension of the water itself, a fusion of machine intelligence and environmental adaptation. One prototype in particular, nicknamed the Hydra, demonstrates just how far Maxwell has pushed marine design. In test footage, it's seen skimming over choppy waters at speeds that would typically swamp traditional crafts, yet maintaining a steady, almost floating motion. When it changes direction, the pivot is instantaneous. The wake it leaves is minimal, the noise almost non-existent. For a moment, it's hard to believe it's real. And then there's versatility. These vehicles are modular. They can operate as high-speed reconnaissance craft, leisure transport, emergency rescue units, or even cargo haulers. One moment it's navigating narrow mangrove channels, the next it's traversing open ocean, all without compromise. But Maxwell's ambitions go beyond performance. Durability, sustainability, and adaptability are core principles. The materials used are lightweight but incredibly strong, corrosion-resistant composites that withstand saltwater and storms. Energy systems are designed not just for power, but for efficiency and environmental impact. Every vessel aims to redefine what a watercraft can do without destroying the ecosystems it moves through. Then comes the shock factor. Some prototypes are equipped with advanced energy manipulation technology, a way of reducing drag using controlled water flow fields, essentially allowing a boat to slice through water in ways conventional physics would suggest is impossible. Early observers liken it to watching a knife pass effortlessly through water without resistance. The implications are huge. Faster travel, lower energy costs, safer emergency operations, and completely new marine applications. For commercial shipping, for coastal rescue missions, for military logistics, the potential is staggering. And Maxwell isn't just showing concepts. These vehicles are operational. They float, they move, and they outperform almost everything in existence today. Observers who have witnessed tests describe it in one word: alien. Not because it's extraterrestrial, but because it behaves in ways no one has seen before. It challenges every assumption about marine transport, from energy efficiency to maneuverability to endurance. And yet it is entirely human-made. The question now becomes, what's next? How far can Maxwell push these systems? Will we see high-speed water corridors powered by hybrid energy vessels, autonomous coastal rescue networks, or even modular ocean exploration platforms capable of operating in the harshest environments with minimal human intervention? Because one thing is clear, Maxwell Chikumbutso isn't just building boats. He's building the future of water transport, and the world is only beginning to understand it. And just when you think you've seen it all, one of the Hydra prototypes performs a maneuver that defies expectations entirely, a near-vertical ascent out of choppy waves, hovering for seconds before dropping silently back into the water, almost like it's flying. That moment changes everything. Suddenly, the line between sea and sky seems less distinct, and the imagination becomes the only limit. The moment that Hydra hovered above the waves sent shockwaves through the engineering community. Observers could barely comprehend what they were seeing, a water vehicle performing vertical maneuvers more commonly associated with aircraft than boats. Cameras captured the craft ascending smoothly, holding position for several seconds, then descending without disturbing the surrounding water, a feat that seemed to defy every textbook rule of hydrodynamics. Engineers on site were taking notes frantically, their faces a mix of awe and disbelief. One remarked quietly, "It's not just advanced. It's rewriting everything we know about fluid mechanics." Meanwhile, Maxwell watched from the deck of the launch platform, calm but focused. He knew the significance. This wasn't just a demonstration of raw power or speed. It was proof that marine vehicles could evolve beyond the physical constraints that had bound them for centuries. And the implications were enormous. Because this level of control over water flow and propulsion opens doors previously thought impossible. Rescue teams could deploy vehicles in hurricane-force waves, reaching stranded civilians where helicopters can't go. Coastal nations could deploy fast, silent patrols that require minimal fuel and leave no detectable wake. Commercial shipping could be revolutionized with craft capable of sustained high speeds, low energy consumption, and minimal environmental disruption. Even more astonishingly, scientists speculated that the energy systems Maxwell was employing could be scaled. What if the same technology powered modular ocean research stations? Or autonomous underwater vehicles that could explore the deepest trenches without resurfacing for weeks? The potential applications stretched across civilian, military, and scientific domains. But with every revelation came a new set of questions. How exactly does Maxwell's propulsion system reduce drag so effectively? How does it maintain stability during vertical maneuvers in rough seas? Could these techniques be adapted to other vehicles, aircraft, spacecraft, even land transport? The demonstration continued. The Hydra skidded across the water at incredible speed, making sharp turns that would have capsized traditional boats. Observers noted the vehicle seemed almost aware of the water itself, adjusting its hull in real time to the subtlest changes in current and wave pattern. Maxwell's team had hinted at autonomous adjustments before, but seeing it in action was another level entirely. One of the most remarkable moments came when the craft transitioned seamlessly from high-speed horizontal movement to a hovering vertical position, then back again, all without visible propulsion systems kicking in. Some engineers whispered the word anti-gravity, not because it was literally defying gravity, but because it behaved as if conventional forces didn't fully apply. The media coverage, when it began to leak, painted the scene in almost mythical terms. "A boat that flies," one headline read. "The vessel that shouldn't exist," another said. But Maxwell remained focused not on headlines, but on pushing the technology further. He knew the Hydra was only a glimpse of what was possible. The next phase of testing would take the craft into deeper and more treacherous waters, open ocean, extreme currents, even storm conditions. Maxwell's goal was to prove that these vehicles could operate anywhere humans rely on water for transport, trade, exploration, or rescue. And if the test succeeded, it would signal the beginning of a new era in maritime technology. At the heart of it all, Maxwell's vision was clear. Water vehicles should no longer be constrained by tradition, fuel inefficiency, or conventional engineering limits. They should be intelligent, efficient, adaptable, and capable of doing things that once seemed impossible. And as the sun set over the experimental waters that evening, the Hydra floated silently, a sleek silhouette against the horizon, a symbol of innovation unbound, and a hint of a future where humanity's relationship with water transport would never be the same. As night fell over the test waters, Maxwell's team prepared the Hydra for a more extreme trial, a high-speed run through a simulated storm environment. Waves surged against reinforced barriers, and wind machines created gusts strong enough to challenge any conventional craft. The Hydra sliced through the chaos like it was skimming a glass pond. Cameras captured every angle, spray deflected effortlessly, the hull remaining perfectly stable, sensors adjusting continuously to the violent water movement. Engineers monitoring remotely could hardly believe the real-time telemetry. Speed, stability, and energy efficiency all exceeded the theoretical limits of conventional naval engineering. Observers who had spent decades in maritime innovation whispered among themselves, "It's not just faster, it anticipates the ocean." The autonomous systems weren't reacting, they were predicting. Every swell, every undercurrent, every sudden gust was accounted for before it could affect performance. The craft didn't just navigate water, it seemed to understand it. Maxwell's vision was becoming reality. He had repeatedly emphasized that innovation should not just break records, but redefine utility. This storm test wasn't about impressing spectators. It was proof that these vehicles could operate safely in conditions that had previously grounded fleets of ships and boats. By dawn, the Hydra had completed its trial. Not a single system failure, not a single deviation from course, and no energy reserves depleted beyond expectations. The craft had achieved what engineers called a self-sustaining operational loop, using energy harvesting modules to recover lost power from water movement, maintaining peak performance without refueling. News of the trial began to spread quietly among the marine engineering community. Whispers turned to online forum posts. Analysts started to compile comparisons: traditional boats versus Maxwell's craft, storm test data versus real-world vessel performance, energy consumption models against autonomous navigation metrics. The consensus was growing. This was a leap not just in speed or endurance, but in the fundamental relationship between humans and water vehicles. At the same time, governments and private research firms began reaching out to Maxwell, not for purchase, but for collaboration. They wanted to study, understand, and eventually integrate these innovations into broader applications: disaster relief, coastal patrol, commercial shipping, and even oceanic research platforms. Maxwell, however, remained cautious. He understood the stakes. This wasn't just about creating faster boats or smarter systems. It was about shaping a new era of marine technology. If misused or monopolized, the potential impact could be both revolutionary and disruptive. And yet, in the quiet moments after the storm trials, Maxwell allowed himself a small smile. Each prototype, each test, each innovation confirmed something he had believed since the very first sketches: that humanity's potential to master water, safely, efficiently, and intelligently, was only beginning to be realized. Even as he looked out over the calm waters now returning after the storm, his mind was already on the next challenge: scaling these systems for longer oceanic voyages, integrating modular designs for multi-purpose use, and exploring hybrid propulsion methods that could one day make fuel dependence obsolete. The Hydra was only the beginning. The next phase of testing involved coordinated operations between multiple Hydra prototypes. Maxwell's team deployed 3 vessels simultaneously across a wide oceanic range, each communicating autonomously to maintain formation, avoid collisions, and adapt to waves in real time. It was the first practical demonstration of what Maxwell referred to as a cohesive marine swarm. From a control deck, engineers observed the vessels moving like a single organism. When one Hydra encountered a rogue wave, the others adjusted instantly, slightly shifting speed, yaw, and pitch to maintain the formation. It wasn't programmed to mimic this behavior. The AI on board predicted and harmonized movement across all units, effectively treating the ocean as a shared medium for collective navigation. The implications were staggering. Search and rescue operations could deploy fleets of autonomous craft capable of covering vast areas efficiently, rescuing stranded vessels, or delivering supplies to disaster zones without human operators risking their lives. Commercial shipping could see a future where cargo fleets travel in perfect coordination, reducing fuel consumption, preventing collisions, and even optimizing ocean traffic flow globally. But Maxwell's ambitions didn't stop at surface coordination. Some prototypes were equipped with submersible modules, allowing them to temporarily dive below the waves, scan for underwater obstacles, or survey ecosystems. Cameras and sonar feeds streamed back in real time, showing coral reefs, deep water trenches, and schools of fish, without disturbing the environment. It was a fusion of speed, intelligence, and ecological sensitivity that was unheard of in marine engineering. As the fleet completed its transoceanic simulation, the team began testing energy regeneration in extreme conditions. Even during high-speed maneuvers and abrupt directional changes, the vessels harvested kinetic energy from the water itself. Systems that once required external charging now ran entirely self-sufficient for prolonged periods. Analysts watching the telemetry could hardly hide their astonishment. Some commented quietly, "It's not just innovation, it's autonomy beyond anything we've seen." Maxwell observed all of this silently, yet his eyes hinted at anticipation. Each trial answered one question but opened dozens more. How far could these fleets travel? How could they scale for global maritime operations? Could the same principles apply to inter-island logistics, polar research, or offshore energy installations? Outside observers began documenting every movement. Satellite feeds, drone cameras, and independent journalists captured footage of vessels that seemed to defy traditional naval physics, gliding across tumultuous waves as if the ocean itself had become cooperative. When the footage leaked to global tech forums, reactions ranged from disbelief to awe. Marine engineers debated furiously, questioning whether what they saw could exist under current fluid dynamics models. Governments began to take note, quietly sending envoys and technical observers, curious whether Maxwell's technology could be adapted for humanitarian aid, Coast Guard missions, or even naval applications. Yet Maxwell remained deliberate. He knew the potential misuse of such vessels, and he was determined to maintain control over how this innovation entered the world. By now, the Hydra fleet had demonstrated extreme speed, vertical maneuvering, storm endurance, autonomous coordination, submersible capabilities, and near-complete energy self-sufficiency. In essence, the vessels represented a new paradigm in marine transport. And just when global attention began to intensify, Maxwell hinted at the next evolution: Hydra vessels capable of semi-aerial transition, vehicles that could lift partially out of water, skimming waves at speeds impossible for traditional boats, combining aerodynamic lift with hydrodynamic efficiency. If realized, this would blur the line between marine and aerial transport, opening entirely new possibilities for travel, logistics, and exploration. Months later, the next evolution of the Hydra fleet was ready for its first semi-aerial test. Maxwell's team had modified the hulls with retractable fins and adaptive airfoil surfaces, allowing the vessels to lift partially out of the water, reducing drag and increasing speed dramatically. On the day of the trial, engineers and invited observers lined the cliffs overlooking the open ocean. Drones hovered above, cameras rolling from multiple angles. The Hydra glided into the water, engines silent, sensors active, moving faster than any craft of its size should have been capable of. Then, in a single, fluid motion, the craft began lifting out of the waves. Spray evaporated almost before it touched the surface, and the vessel skimmed across the water like a hovercraft, yet without air cushions. Observers whispered in disbelief. The semi-aerial lift wasn't just fast, it was precise, stable, and almost eerily silent. Maxwell's assistant noted in real-time telemetry, velocity exceeding projected hull speed by 40%. Lift sustained. No destabilization. Energy recovery at peak efficiency. As the Hydra executed a series of maneuvers, tight turns, sudden accelerations, and vertical hops over waves, it became clear that the line between sea and air had blurred. Traditional naval charts, wave height predictions, and hydrodynamic models were inadequate. Engineers struggled to reconcile the data with known physics. The demonstration ended with the Hydra coming to a flawless stop just meters from the shoreline. Cameras captured the crew's stunned reactions, and for a moment, the ocean itself seemed transformed, not as an obstacle to traverse, but as a playground for a new generation of vehicles. Global media caught wind of the trial within hours. Headlines ranged from incredulity, "Boat that flies," to cautious excitement. Revolutionary marine tech could redefine global transport. Analysts debated potential applications: ultra-fast coastal rescue, disaster relief missions, high-speed freight transport, and even eco-friendly passenger ferries. Maxwell, however, remained focused on the long-term vision. These semi-aerial capabilities weren't just about speed. They were about creating versatile, adaptive vehicles capable of operating in extreme environments, storm-lashed coasts, polar seas, and even remote island chains. He emphasized that accessibility and sustainability were just as important as performance. The semi-aerial Hydra also revealed possibilities for fleet coordination on a global scale. Maxwell envisioned autonomous convoys traversing oceans with minimal human oversight, skimming waves at high speed while harvesting energy from both water and wind. Disaster zones could see rapid deployment of supplies, and environmental monitoring missions could cover vast areas without refueling. International observers quietly began drafting proposals for partnerships, research exchanges, and deployment scenarios. Yet Maxwell remained cautious. He understood that once such technology entered global circulation, control, and ethical use would be the greatest challenge. As the sun set over the trial waters, the Hydra fleet rested in formation, partially submerged, partially hovering above the waves. The vessels glowed faintly from onboard energy cells, a silent testament to what human ingenuity could achieve when tradition and imagination collide. Maxwell stepped back, surveying the horizon. The ocean, once a boundary, now looked like a frontier. And in that moment, it was clear. The future of water transport had arrived, and it belonged to those who dared to rethink the rules. In the weeks that followed, Maxwell's semi-aerial Hydra fleet captured global attention. Engineers, scientists, and media outlets documented every maneuver, every innovation, every breakthrough. The world realized that marine transport was no longer bound by the limits of conventional physics. It could be fast, intelligent, adaptive, and sustainable. Governments and corporations approached cautiously, eager to study and collaborate, but Maxwell remained focused on his principles: accessibility, ethical use, and pushing the boundaries of what was possible without compromising safety or the environment. The Hydra fleet became more than a demonstration of technology. It became a symbol of human ingenuity, of imagination meeting engineering, and of the daring vision required to redefine entire industries. And as Maxwell looked out over the calm waters, now dotted with his revolutionary vessels, he knew one thing for certain: this was only the beginning. The future of marine transport had arrived, and it would never look the same again.